in the last class we had basically achieved the derivation of the Lagrangian equation. So, what actually did you do? If there are n number of bodies in a system, each marked as j, then for each equation in the Newtonian way would be m q double dot is equal to the force, the applied force plus the constant force, sorry, F c. This would be vector, this would be vector, and all that will have the j subscript. That was the Newton's. Now, you can see that if there are say 25 bodies in a system, you would need 25 such equations, and then you will have to, you will get the set of differential equations as that is 25 set. But that 25 could be in a 3-dimensional space. So, how many coordinates do you really need? 3. And how many equations do you really need? 3. If there are holonomic constants, then it even goes to less. So, that was one problem with the Newton's equation, and from there we had obtained the Lagrangian equation as d dt of this is the Lagrangian function with respect to q dot here minus Lagrangian function. So, this is the Lagrangian way. And these two forms are mathematically equivalent, because they yield the same differential equation. We had seen that starting from here we have arrived at this. Now, these are, each equation will have the subscript I. This I then represents the identifier of the new coordinates, the generalized coordinates. So, if there are n number of such generalized coordinates, which is the total number of necessary configuration variables minus the number of holonomic constants, this would be that many number. Okay. Now, let us try to understand how this equation can be used, but first what does this consist of? The Lagrangian function is the kinetic energy minus the potential energy, that is what we said. And in the potential energy, we said that at least we have gone up to that extent where we said that at least we understand how it is for the gravitational potential, we understand how it is for the electrostatic potential. So, that much we understand, but in general that could, a body could be attached to other bodies through spring like elements, through other kinds of elements. So, let us understand that first. Now, suppose you have a spring and this end is being pulled, and from the unstretched position it has been pulled by an amount q, which is the position coordinate. Then what is the energy stored in this? So, energy stored is half k q square. Now, notice that this has the form of the potential energy. Why? Because if this is the potential, then is just k q, and k q is the amount of force that we expect, right. So, you get the, and why is this minus? Because you are pulling in this direction and the force is applied in the opposite direction, that is why this minus comes, has to come. So, you have the force obtained as the gradient of the potential. So, the energy stored in the spring is actually potential energy. Is that clear? So, if a system has both springs and gravitational energy stored, so the total potential energy would be the potential energy stored in the spring as well as the in the gravitational energy. And this potential energy is a scalar, just a number, it has no direction. So, if something is stored here, something is stored there, something is stored there, just add them up, that is it. That gives you the total potential energy, that is one advantage. Let us illustrate with a very simple system, the simple oscillator, how this can be used. Suppose there is a spring here connected to a mass. Okay. Simple, no complication. How would you obtain the differential equation in this case? Let us start from the simple system. Yes, we would first say, no, before going into that, let me start from here and illustrate how the process of obtaining the differential equation goes. In case of the Newtonian equation, what did we do? For every mass point, we identified the forces acting on it, and in order to facilitate that, we drew the free body diagram that you probably learnt in the mechanics class, right. So, we drew the free body diagram, then we either wrote force is equal to mass into acceleration, or if we write in the D'Alembert's way, the free body diagram itself contains the mq double dot. So, just balance of the forces. In this case, what we do is, we have already achieved the feat of reducing the number of differential equations using the holonomic constants. So, now if looking at a system, we find that we can define a set of position coordinates remember, position coordinates that are consistent with the constraints. The minimum number of position coordinates necessary to define the positional status of the whole system uniquely, that is it. So, the first step in the Lagrangian formulation would be 1, identify the generalized coordinates. Now, remember, these generalized coordinates, this nomenclature should not confuse you. In case of a system like this, what can be the generalized coordinate? Here is a body. In the Newtonian way, it has x, y, z coordinates. In the Lagrangian way, I do not need the y and z coordinates, that is it. We will say that from the unstressed position of the spring, I will measure the variable q, that is it, just one necessary. So, that is the generalized coordinate. In case of the simple pendulum, what is the generalized coordinate? Simple pendulum, suppose it is a planar pendulum, which means that the first holonomic constant forces it to move on a sphere, and the second holonomic constant imposes another plane on it. So, it is forced to move on an arc. If it moves on an arc, then what is the minimum number of position coordinates can I define that is consistent with the constant? Just one, and that is simple theta. So, whatever follows from your common sense, that exactly is the generalized coordinate, it just goes as a name. Fine. So, you have the number of generalized coordinates. Normally, they would be denoted as qi, that is the way we normally define. So, even if something is theta, we can call it q1, q2 and all that, but sometimes we might, in order to make the identification easy, continue with the alpha, beta, theta and whatever. but always remember that this is the coordinate. Well, once we have identified this, then express the kinetic energy and the potential energy in terms of okay. So, we have the position coordinates. Now, express the potential energy and the kinetic energy in terms of this q I and q I dot. Then that is it. Then we just substitute in the Lagrangian equation. Let us illustrate. Start with this problem. Number 1, identify the generalized coordinate. We have identified only one. Yes.
Sir, if you can't identify the generalized coordinate, will it matter? The equation
No, it will matter. His question is, if we can't identify the generalized coordinate, will it matter? Okay, one clarification might be necessary. In a system, there might be some generalized coordinates that are spherical, there might be some generalized coordinates that are linear, and also in electromechanical system there can be some generalized coordinates that are in the mechanical domain, some generalized coordinates that are in the electrical domain. It is possible, but you will have to identify. That is the first step. So, that has to be identified, and I will work out here many problems, so that you will after some time be comfortable with it. Okay, once you have done that, express the kinetic energy and the potential energy in terms of q and q dot. So, you can easily do that. If the velocity is q dot, then t is half m, right. The potential energy is half k q square, simple. So, the Lagrangian is t minus v half m q dot square minus half k q square, right. So, the derivative of Lagrangian with respect to q dot is right, and the derivative of the Lagrangian with respect to q is minus k q, right. Once you have written this, we have to substitute here. So, let us substitute. You get d dt of Lagrangian dou q dot minus, substitute this, you get m q double dot here, because it is again derivative with respect to time, plus k q equal to 0. That is the equation of the system. Okay. Pretty simple really. Well, you might say that as yet the advantage of the Lagrangian form, Lagrangian way of writing the equation vis-a-vis the Newtonian form is not very clear, because we could have done this way, that here if I pull it a bit, then the mass is acted on by a force like kq in this direction. So, kq is the force acting on it, and that is mass into acceleration. That is exactly what you have written here. Yes, right from here it may not be all that clear. Only thing is that in the Newtonian way, logically you will have to write the equations for all the directions, but now you know that they are not moving in all the directions. So, exactly from this one it may not be all that clear. So, let us now handle this problem which we had done earlier. Just turn the page where we have earlier obtained the differential equations by the Newtonian way. There the tension appeared, and it had to appear because that is a force acting on the body, it had to appear. But now in the Lagrangian way we will not bother about it at all. Why? Because that is a constant force and we have eliminated the constant force altogether from the formulation. So, we will forget about it. So, the generalized coordinates, is what? Theta. The generalized velocity, remember one thing, the generalized velocity is simply the derivative of theta, derivative of the generalized coordinate, not the actual velocity of the body. The actual velocity of the body is so if this is L, then L theta dot, but we are not talking about that. Your generalized velocity is simply the derivative of this. Fine. The next step is to obtain the kinetic energy and the potential energy. The kinetic energy is, what is the velocity of this fellow? It is say this length is L. So, it is L theta dot is the velocity. So, half m L theta dot square, here, and your potential energy is, suppose I measure from here, measure from here how much it is below. Then if this is theta, then this height is L cos theta. So, negative of that minus L cos theta, right, sorry, MGL. So, yes, L cos theta MG has to be there. So, your Lagrangian function is T minus B half m L square theta dot square plus L mg L cos theta. So, your derivative of the Lagrangian with respect to theta dot is m L square theta dot. The derivative of the Lagrangian with respect to theta is, do it, it will be m g L cos theta minus sin theta, the moment you have this, you can easily, is there space here? Yes, you can write down the differential equation. Derivative of this with respect to time, which is m L square theta double dot, minus of this, so it's plus m g L sin theta equal to 0. M cancels off, L, one of L cancels off, so you get theta double dot is equal to minus G by L sin theta. That is the equation. Clear? So, that is how we write it, and you see that we do not need to write 3 equations, we do not need to consider the tension, it becomes simple. Clear? and that is the main advantage of the Lagrangian form. Now, if the advantage is salient even for such a simple system, for more complicated system it will be far more salient. Let us try to illustrate some of that. Okay. Now, you have while talking about the constants, we had considered this kind of a situation. Okay. We had considered this. So, let us obtain the differential equation of this. Here you would notice that here is a tension, here is a tension, and we had argued that this tension does work, this tension also does work, but put together they do no work. Anyway, that is not important. What is important is that written in the Newtonian way, you will have to consider these two tensions, and written in the Lagrangian way, we can right at the beginning forget about them. So, first question, how many generalized coordinates do we need in this case? Only one, because the moment it goes up, it has to go that amount down. So, both these positions are given by just one body, was one coordinate, and let that be starting from say this position. We can say this is Q, right. If the total length here is say L, then this becomes L minus Q. So, the generalized coordinate is consistent with the constant is Q, fine. Now, write the kinetic energy and the potential energy. So, what will be the potential energy? Potential energy is the potential of this body and the potential of that body taken together. So, you have yes minus let us say let this be m1 and let this be m2. So, you have minus m1 g and q for this one, and minus m1 m2 g L minus q for this one. Okay. So, that is the total potential energy, and the kinetic energy is they of course move together. So, if this fellow moves with the velocity q dot, that fellow also moves with the velocity q dot, we can simply add them up. So, half m1 plus m2 q dot square. So, the Lagrangian is half m1 plus m2 q dot square minus plus m1 g q plus m2 g, will it go out? No, L minus q. Okay. Now, let us differentiate. So, is m1 plus m2 q dot, and the derivative with respect to q is, let us see this term m1 g, this fellow cancels off, this fellow vanishes. So, minus m2 g, right. So, these are two parts, one the fixed part, another the variable part, that is what remains. So, ultimately, since we have space here, we can write the derivative of this with respect to time m1 plus m2 q dot, it becomes q double dot minus this. So, minus m1 g plus m2, right, that is the equation. Okay, one thing might be worth mentioning, that in the last problem that we solved, the simple pendulum, we had written the potential as minus mgl cos theta, taking this point as the datum. Suppose some of you say, no, I do not want to take that as the datum. After all, this fellow comes here, that is the minimum position, I will take that as the datum and measure it from there. Yes, you can do that. In that case, this total length is here L, and how much is the elevation? L minus this. Do that, no problem, L minus L cos theta. But then what happens in that case? Just do it. It will be L minus L cos theta, this whole thing mg. You would notice that this this will have two components, one a constant component mgl minus mgl cos theta. When you take the derivative, this fixed term vanishes, and therefore that does not appear. So, it does not really matter where you take the datum. Is that clear? So, that is up to you, wherever you want you can take. Fine. Okay, now let us go to a slightly more involved problem. Think of this. Suppose you have a pendulum as before, but here the point of suspension is moving like this. If you actually simulate and see its behavior, such a thing, you would find that it has a very complicated behavior, very complicated motion. So, let us try to write down the differential equation that can capture that motion. So, this length is L, here is your M. We would need the x coordinate, the y coordinate, because this fellow is moving in the x coordinate. So, here is the x and here is the y. Fine. Now, x is if this is theta, x is L sin theta. No, let us redefine, because things are happening in this direction. Let us call it y and let us call this x. Then y is equal to L sin theta and x is equal to L cos theta. Okay. Now, your additional thing is adding to the y. Okay. Suppose that suspension's movement is called ys, and this fellow's position is y. If you have this, if this fellow is not moving, then you can say your x dot is minus L sin theta and y dot is L cos theta, right? Sorry, into theta dot. Sorry. So, these two are the velocities of this fellow, and we have to add to that the velocity here. In order to obtain the actual velocity of the bob, it is, if this were not moving, whatever the velocity would be plus the velocity that is imposed on it. That will be the easy way of looking at it. Fine, fine, that is what we will do. So, ultimately when we have obtained this, then the kinetic energy is half m v square. So, we have to say half m, and the v is v square is x square plus y square, x dot square plus y dot square. It would be then x dot, there is nothing happening in the x dot direction, x dot square plus y dot plus y s dot square, right. What you have done in this direction, the movement, the velocity was y dot, added to that you have got some velocity here. So, this fellow will actually move with this velocity in the y direction, and x square plus y square is the actual velocity square. That is what we need, clear. So, let us break it up. You have half m x dot square plus y dot square plus y s dot square plus twice y dot y s dot. Now, we know what these guys are in terms of theta, because that is what we want to write it in. So, we substitute m, x dot is x dot square minus goes of L square sin square theta, theta dot square, we have already done it, plus this is L square cos square theta, theta dot square plus y dot s square plus yes, twice y, this comes down, twice y is this fellow y dot L cos theta, theta dot times y s dot. Has it gone off the screen? Let us move it a bit, then you will be able to see. Yes, twice L cos theta, theta dot y s dot, right. Happy? What can we do from here? What can we do from here? Wait. So, it is done essentially. These two can be put together, because sin square theta cos square theta is 1. So, that can be simplified. So, T is half m L square theta dot square plus these two terms, they remain, plus y s dot square plus twice L cos theta, theta dot y s dot. Happy? Look, the procedure is pretty straightforward. What we have done, we have identified what the velocity would be, and accordingly we have written in terms of the actual generalized coordinate. These are this theta, and of course y s also has to be one coordinate. So, we have written the T, and then we have to write V, the potential energy, and the potential energy is pretty simple, because the amount of potential energy is in no way different from for the simple pendulum. Simple pendulum we had written minus mgl cos theta. So, minus mgl cos theta. Okay. So, your Lagrangian term becomes this whole thing half m let me multiply, let me get rid of this bracket. So, half m L square theta dot square plus half m y dot s square plus now 2.5 consists of m l cos theta theta dot y dot s, that does it, t minus v. So, plus m g l cos theta. Okay. So, that is the Lagrangian. So, see, I am doing absolutely algorithmically. I know that I have identified the coordinates, and after that I am proceeding algorithmically. All these are simple algebra, no complication really, even though this may look a bit longish. So, you have with respect to with respect to what will you differentiate? Theta. So, you have theta dot, and we will have to differentiate with respect to theta. Now, this becomes m l square theta dot, right. This goes off, this remains. So, this was what? This plus, this is not there. So, you have if you differentiate it, it will be plus m l cos theta y dot s. Okay. This goes off. Now, when we differentiate with respect to theta, this goes, this remains, yes, m l theta dot y dot s, and then cos theta. So, you have yeah, sin theta minus, yes, no, I am talking about this term, here minus, yes, okay. Fine. Now, we have to differentiate these two, and that is it. So, can you write down now, starting from here? Now, we have to write down the d dt. Let me explicitly write it. Okay. So, you have to say d dt of this term, m l square theta dot. I am doing this expressly because people make a mistake at this stage. Right. Now, you differentiate this. If you differentiate this, what do you get? Firstly, you get m l square theta double dot. Now, here are two quantities that are depending on time, and therefore, you have to be careful in differentiating this term. You have to say plus m l cos theta y double dot s plus m l y dot s sin theta. ठीक है? Into theta, right? And this is the crucial thing that people miss. So, plus m l theta dot y dot sin theta plus m g l sin theta equal to 0. Done. That's what I am looking for. What cancels?
ml y dot s sin theta theta.
Huh?
Second and fourth. The third and the fourth term will cancel.
These two cancel off, no?
Yes, sir.
Yes. So these things, three things remain. Okay. Then we can cancel certain things. So things become simpler. Theta double dot plus g by L sin theta. These things were there in the simple pendulum. That is why I wanted to write it this way. Plus 1 by L cos theta y double dot s equal to 0. That becomes the equation. Can you now write down on your copy, if this y s happens to be a sinusoidal oscillation, then what will this equation be?
So in this problem, there will be another differential equation with respect to ys.
No, that is the externally imposed motion. That is why it is not an independent degree of freedom of the system. That is why it is not necessary at this stage. Her question is that won't this become another coordinate? No, it is not necessary, because it has no external internal degree of freedom. It is moved by somebody. Ys is being imposed by somebody. So the system has no freedom in choosing that. That is why you do not need that as a coordinate. That is imposed by somebody.
But when we
Even without solving the differential equation, you know where ys would be at any point of time. That is why. Okay. So you need a coordinate if, in order to find out what that coordinate value will be at a specific point of time, you need to solve the differential equation. But in this case, you do not need to.
and sir, if in this case the mass had here we have considered it massless, right?
Which one?
Which is
This
moving.
fellow.
Yes, sir.
Yes.
If it had a mass, then kinetic energy we would have considered a term.
Yes.
For that?
Her question then is, if this fellow were a mass, then somebody would not be able to move it just like that. It would be application of a force, and this will then have its own dynamics, right? In that case, yes, you need to.
And in that case, we consider another set of differential equation with respect to ys.
Yes. Yes. In that case, ys becomes an independent coordinate of the system, an independent degree of freedom. But in this case, the way we have defined the problem as yet, it does not become. Okay. Yes, if this fellow had a mass, you are applying a force, and then the mass moves depending on the force and its own dynamics, because this is being pulled by this fellow also. So in that case, you do not know beforehand what the position of this mass is at any point of time. You need to solve the differential equation for that, and for that it becomes a independent coordinate. Fine. So in this case, as I told you, in case ys is a sinusoidal function, say ys is equal to, say, a cos omega t. Can you see? Yes. In that case, what is the equation? Write down yourself, because most logical way of moving this fellow would be a sinusoidal oscillation. So if that happens, then what will be the equation? This will just become a omega square, cos becomes sine with a negative sign here, and that is it. Only I wanted you to note that this is a double derivative, so you will need to take a derivative twice. That is it. But if it is an unknown quantity and something is imposed from outside, then it is simply this equation. Okay, now are you now comfortable with this idea? How the equations are derived? Note one thing, that you are getting second order differential equations. Along each position coordinate. And so far we have considered problems with just one coordinate. Let us now take the next step. Let us take a simple next step to a system where there are more than one position coordinate. Say again, let us take the pendulum, but let us make it a little more complicated. Suppose here it is, but instead of just being connected to a, here is a spring and then you connect it. क्या हो गया? What has happened because of the spring? There is another degree of freedom in this direction. There is another degree of freedom in this direction. Now you really have to apply your brain a bit in order to identify the generalized coordinates. Karo. Here is your theta. Now you would notice that there are many ways of defining the position coordinates. Theta is a natural choice, all right, but how will you in the radial direction there is another degree of freedom I can see, but how do you define that? There are various ways of doing it. You might say that distance is measured from here, that is it. You might say that no, let it hang freely here in this position, then it takes a particular length of this. Remember, in this position it is not unstretched, it is already stretched, but let that be the datum, and from there I will measure the difference. You could say that, and they will actually make no difference. They will actually make no difference. So in order to do that, let us do it that way. So what did we say? We said that when it freely hangs vertically, then your position is the datum position. And in that position, suppose it came here, and this distance is say a. And then this distance is the deviation from there. So distance is a plus the coordinate that we are talking about r. We can do it this way. That also uniquely defines its position. Does it not? Plus theta. Theta has to be there as one of the coordinates. So r and theta. So then generalized coordinates become r and theta. Okay. Now in terms of this r and theta, what is kinetic energy and what is potential energy? That is what we will try to write. Kinetic energy will be relatively simple to write, potential energy will require a bit of thought. The kinetic energy is half m v square. So half m we will write first, and then we will try to figure out what the v square is. Now notice that there is a component of the motion in the radial direction, and there is a component of the motion in the circumferential direction. So if you can identify these two, then it will be simply this square plus that square. So in the radial direction, the velocity is r dot, yes. So it is r dot square plus, yes, a plus r theta dot whole square of this. So both these have the squares. Done. The potential energy in this case, there are many sources of the potential energy. That is the fun of this problem. 1, it is contributed by the gravity. 2, it is contributed also by the spring, and they have no difference. We will simply add them up because they are scalars. That is the advantage. Fine. So how do we go about it? Notice, let us start the argument from the position that it is unstretched. If it is unstretched, it has some position, but from there it has already here it has already been elongated by application of a force mg. So how much has it already elongated? Mg by k. It has already elongated in this position by mg by k. And I am now counting the difference from that position here, and therefore what is the actual elongation? Mg by k plus r. Okay. So the actual elongation is, let me start from here, actual, sorry, mg by k plus r. That is the amount, the actual energy. So the potential energy in the spring is half k into actual elongation square. So you have so that is the amount of energy in the spring. Right? When it is hanging vertically in this position, then the gravitational energy is 0, and we are taking that as the datum and counting gravitational energy from there. So how much has it gone up from there, that position? This much is a plus r cos theta. So a minus a plus r cos theta is the amount by which it has gone up. So V gravity is mg times this amount, which is a minus a plus r cos theta. Is the line of argument clear? The moment you have identified these two, the total potential energy is the addition of these two, and the Lagrangian is T minus that, and the rest is simply algorithmic. You do not have to apply your head, just algebra. Clear? So you obtain that differential equation starting from there. Clear? There is the rest of the problem is simply in a routine procedure. You do not have to really apply your head a lot for the rest of this problem. Clear? Fine. Bring that in the next class. Thank you very much. Let us stop here.